Greetings, Bill here. Time for another video. Cup of coffee. Couple of things. Let's see. I'm making this video on Thursday afternoon, so we had lab yesterday, and I tried to flash a light, and it didn't flash. Kind of embarrassing. It turned out that the code was absolutely fine. The problem was that I was flashing the light too quickly. You may recall we wrote a loop that caused a 1 microsecond delay. And then we went ahead and we wrote some code that basically turned the LED on for a microsecond, then it turned it off for a microsecond. So that means that it was flashing on and off 500 times in a second. That's just a little bit too quick to actually get an on-off effect. LEDs, very much like regular electric bulbs, sort of run on the notion of heat. You heat them up, and what happens is from the heat it generates light. If you're turning the thing on and off 500 times, basically what happens is you're not giving the bulb enough time to cool off. So that's why when we did it, the thing looked like it was lit up the whole time. Well, in fact, it was lit up the whole time, but half of the time there was no power to it and it would have gone off. Later on in the day, I changed it so that the light was flashing on and off. I think it was once every 1/10 of a second. Then you could actually see it. So the purpose of this video today, I want to talk more about timing loops. Some of this is going to be a little bit of review that we've seen, but I want to talk about how we can write longer timing loops. And interestingly enough, in a couple of weeks, this is all going to be a very moot point because we're going to learn that the chip has a timer in it, so that you can say to the chip, please, please measure me a half a second interval, or measure me a 100 millisecond interval. And not only can we say measure me that interval, but when you're done, we can say to it, please sound an alarm. That sounds a little bit strange. The alarm is actually an interrupt, and that's another topic that we're going to have to talk about. But we're going to walk before we run. We have to learn a few things about this chip. So the purpose of this tape today and this video is to show you how to develop some different timing loops. And you will need this on your first assignment. Now, before we proceed, I think I've mentioned to all of you that I have just returned from spending a wonderful year living in Namibia. So I take this as a nice segue. We're going to have a commercial interruption here, and I'm going to show you some video from Namibia. See you in a minute.
Wabitiri kwa ronga mwana koi mwana. We wabitiri we. We kuronga na we. Awe mapepe kuna kukuneda tukusikwa pisura pano. Hela. O marukia ya mwana kulimwanya. Nomi papa.
How cool is that? For those that are interested, those were, whoops, my screen is upside down. You can't tell that. Those were Kavango dancers. Kavango, they come from the Rundu region. That is in northern Namibia. And maybe I'll show you some other stuff some other time. Okay, what I want to do here, we don't need this taking up our view. Let's get it out of the way. I want you to recall something that we did in class previously. We did something like the following. We said move literal to W, 0 hex, FF, and then we move that into some memory location. And then we did something like the following. We said decrement file, skip if 0, 0 hex 20, and then we said go to here. And what we did is we just put here, right here. Now, by the way, you can put labeled statements on a blank line, and then it would just fall down until it hit the next executable. Now, we went ahead and we did a time analysis of this, and we said that this takes 1 microsecond over here. And we came over here and we said this takes 1 microsecond. And then what we had to do is we had to come over here and we have to analyze this thing. Okay? Now, normally what is going to happen is this will decrement by 1 and it won't be 0. And then it's going to come over here and it's going to say go to here. That is changing the program counter, so that'll take 2 microseconds. So the total here is 3 microseconds for these 2 statements. That's provided that when we decrement this thing, it doesn't hit 0. Okay? So what's happening here is this is going to happen. It's going to happen. Let's just think about it. It's going to happen from 255 down to 254. And then it's going to happen from 254 down to 253. And it's going to keep doing this all the way until it's going to go from 3 to 2. And then it's going to go from 2 to 1. Okay, and then I'm going to draw a line here, and it's going to go from 1 to 0. Now, when it goes from 1 to 0, it's going to skip. Okay, it's not going to do the go to here. But it will do both of these instructions in all of these situations here. And the question is how many times is it doing that? Well, if I come over here and just look at the right side here, it looks like it's going from 1 up to 254. So this is going to be 254 times 3. And that's a 2, carry the 1. That's a 6, carry the 1. That's 7. And then there's going to be the one time over here where this thing actually is 0, and it's going to jump down to here, and that's going to be another 2. Okay, so the total time to execute everything that I see right here is 762 plus 2 is 764, 766. So this is 766, and notice I'm using this Greek letter here, microseconds. Okay, now I want to suppose I want to delay for 1 millisecond, which we know is equal to 1,000 microseconds. Now, we've already written a loop that gets us pretty close to that, and it looks something like the following. We said, let's do a move literal to W, 0 hex, FF. Let's move W to F, move that into register 20, and come over here and say here, and I'm going to have a no-op, and then I'm going to say decrement file, skip of 0, 0 hex 20, and I'm going to say go to here. Okay, so this takes 1 microsecond. This over here takes 1 microsecond. Okay, and what happens over here is we know now that these 3 things are going to execute 254 times. Okay, this is going to execute 254 times. Actually, what's going to happen is this is going to execute 254 times, 254, 254. That's provided that the register 20 isn't 0. So I'm going to get 254 times. What's going to happen is I'm going to get 1, 2, and because this is a jump changing the program register, that's going to give me 2 more. I'm going to get 4 here. Okay, so that's going to be a 6, carry the 1, and that's going to be 21, carry the 2, and it's going to be like that. Okay, now what's going to happen is we are going to get the one time where we come around here, and now the decrement file skip of 0, it is 0, we're going to jump out of here, and that gives us another 2. So now we have a total here of 1 plus 1 plus 1016 plus 2. This gets us up to 1020. Okay, well this is pretty close to what I want to do. I want something that's going to take exactly 1 millisecond or 1,000 microseconds. But we're going to learn something new here. And what I want to do is I want to write a subroutine that's going to do this. And the first thing that you need to know is that in the pick assembler, if I want to call a subroutine, I come over here and I say something like call. And I'm going to say delay underscore, and I'm going to say 1 milli. Okay, and I can stick that anywhere in my program, my executable code that I want to. What I do now to write the subroutine, and it's actually pretty simple, I'm going to come over here and I just have a label, just like a label that I would use for a go-to statement. I'm going to come over here and I'm going to say delay underscore 1 milli, and I just start writing my code over here. Okay, the last statement in a subroutine has to be return. Okay, and the thing to remember about a return is a return changes the program counter. So this, executing this statement right here, takes 2 microseconds. And the other thing to remember over here, this call changes the program counter as well. So this statement over here takes 2 microseconds. So now, if I want something that's going to take a total of a millisecond or 1,000 microseconds, I've got to write code in here that's going to take 1,000 minus 2 minus another 2. I need code in here that's going to be 996 microseconds. Okay? Well, I know that what I need to do is I need to move literal W, and I'm not quite sure what number that should be. I'm going to leave that for a second, and then I'm going to come over here and I'm going to say move WF 0 hex 20. And I'm going to come over here and I'm going to put a label here. I'll just call it here. And we know what this is going to look like. There's going to be a no-op. There is going to be a decrement file, skip if 0, 0 hex 20. And then I'm going to say go to here. So let's do some calculating here now to get this all to work. Remember, we've got to get 996 microseconds. This move long word here, we still have to figure out what value to put in there. but we know that this is going to take a microsecond. We know that this move W to F, that's going to take a microsecond. We know that this is going to loop around. We don't know how many times. It has to do with whatever number we put in here. Let's call that number K. And we basically know that it's going to be, we're going to have K minus 1 times. I'm going to be doing 1, 2, 3, 4. Okay, remember this takes a microsecond. This is going to take a microsecond when we don't skip, and this will take a microsecond, so that's a total of 4 microseconds, and we're going to do that K minus 1 times, and then on the kth time, this thing over here is going to hit 0, so that's going to be another 2 microseconds. So basically what I need to do here now is I just need to solve for K. So it has to be the case that 1 plus 1 plus K minus 1 times 4 plus 2 equals 996. So I'm going to come over here, and that's going to be 1 plus 1 plus, I'm going to have 4K, and it's going to be minus 4, okay, and then plus 2, and that's equal to 996. So 1 plus 1 is 2, and plus 2 is 4, and then I subtract 4. Oh, look at this. This works out very nicely. So 4K is equal to 996, and I've got to do some arithmetic in my head. 4 goes into 9 2 times, so that would be 8, 19. 4 goes into 19 4 times. 16 is going to leave me with a 36. 4 goes into 36 9 times. So the number that I need to do over here is I need to get to 249, and I need to write it in hex. So this is going to be 0 hex, and I don't remember what 249 would be. Let's see, we know that 255 is FF, 254 would be FE, 253 would be FD, 252 would be FC, 251 would be FB, 250 is going to be FA. Everybody following this so far? So what is going to be 1 less than FA? It's going to be F9. So what I need to do over here is I need to move long word 0x F9. Just like that. And now what I have over here is whenever I say call delay 1 millisecond, this over here is going to take 1 millisecond. Well, how cool is that? Okay. Well, one more thing I want to talk about here. Suppose what I want to do, suppose I want to write another thing. I want to say call delay. Let's suppose I were to make it 100 milliseconds. Okay. Now, I've already written something that delays 1 millisecond. So one way I could do this is I could certainly come over here and I could say call delay 1. I forgot what I called it already. Called it 1 milli. And then I could say call delay 1 milli. And I could do this 100 times. And then 1 milli. And then say return. Okay, and this would certainly I think you can see some of the problem here already. Now, if I do this 100 times, this would take 100 milliseconds. But then there's 2 microseconds that I'm adding in here for the call, and there's 2 microseconds I'm adding in here for the return. Okay, that's one possibility. Let's consider another one. So over here, what I want to say is I want to say that there are 4 microseconds overhead, I'm going to call it. And if you want to, you can think of overhead actually being an error. There were 4 microseconds that were off. On the other hand, what I could do is I could come over here and I could say move literal to W, and I'm going to figure out what that should be in a second. And then I'm going to say move W to F. Now remember, in call delay 1 milli, we used register 20 for a counter. So over here we better use a different one. So I'm going to say 21. And now what I'm going to do over here is I'm going to say something like loop. And I'm going to say call delay 1 milli. I'm going to say decrement file skip if 0 21, and then I'll say go to loop. And again, there could be a return here. Now, the advantage of this one, of course, over this one is there are 100 lines in this. Now remember, we're using a chip that has very limited memory when it comes to program memory. There are only 2,048 lines that I can put in a program, and here I'm using up 100 of them just to write a call delay 100 milliseconds. Over here, I'm using far less, 1, 2, 3, 4, 5, 6, okay? Labels by themselves don't take up space. So this is 6 versus 101. Big difference. But we can see that there is more overhead over here, okay? So what's going to happen is this, okay, this gives us exactly what we want in terms of the delay, but now we've got the overhead associated with all of this. Now this thing over here, this is basically going to take 1 microsecond, and this is going to take 2 microseconds, and we are going to put, now remember, what we wanted to do in here is we wanted to call this 100 times. So basically what I need to put in here is the hex value for 100. So that's going to be 0 hex, and let's see, that's going to be 6 times 16 is 96, so that's going to be 64. Okay? But what's going to happen over here is 99 times, okay, I've got the call over here, then I've got the decrement and the go. So this is 1 and this is 2. So that's a total of 3 microseconds that I'm going to do 99 times. So that's going to be 3 times 99. And then there's going to be 2 more over there. So this is going to be 27, carry the 2, is 29, plus 2 is 299. Okay, so the overhead here now is going to be 1 plus 1 is 2, plus 299 is 301. This is going to be 303. So the overhead here is 303 microseconds. Okay, so this is quite a bit more overhead than this one over here. But I want to point out the following now. Okay, we're talking about an overhead. Let's do a little bit of math. So we're talking about, in our shorter version, the overhead is equal to 303 microseconds over 100 milliseconds. Well, 100 milliseconds is 100,000 microseconds. So why don't we just round this off to 300? and we can cancel this out, and we can cancel this out. And the error here is on the order of 3 over 1,000. Okay? Considering that we're using an internal timer in our chip, this is not that great an error. And in fact, it's not something that we should worry about. On the other hand, if you are bothered by all the overhead that's over here, one of the things you could do to cut the overhead down is instead of saying call delay 1 milli, you could call delay 1 milli and do it twice in a row. And instead of putting the number 100 in here, put the number 50 in here. Okay? Now what's going to happen is instead of this being 99, it's going to be approximately half of 99. It'll be about 50. Again, if you could take that another step further, you could have a call delay 1 milli in here, have it in there 4 times. And instead of this being the number 100, it would be the number 25. Then the overhead over here would be 25 times 3. But you can see what happens. I could keep adding more of these, and I'm basically then degenerating into this case over here. I would say that in general, what we've written over here is fine, that this error that we have calculated here for our purposes is going to be negligible. What I'm going to do here, I am probably going to type up just a little bit of, I'm going to type this code up so you can see what it looks like and ship this all off to you. I hope this was helpful. Comments about this video are always welcome. One person previously made reference to the volume, and I hope I've adjusted it accordingly, and we'll see you all later. Bye-bye.